So now that we have looked at perceptron learning algorithm, let's look at logistic regression. And for that, what we'll do is we will go back to Bayesian decisions. So as we talked about this earlier, in Bayesian decisions, we are trying to look at the ratio of two probabilities, and if we take or the difference of logs of two probabilities. So let's look at how that leads to logistic regression type of equation or expression, and then how do we minimize that. So first we will define we'll define a variable a for a binary class classification as the ratio of log odds. Okay, so this is going to be, or the log of the ratio of odds. So this will be log of p of x given c1, p of c1 divided by p of x given c2, p of c2. Okay. So what we can see is that what we want to estimate is p of c given c1 given x, right? And that is based on the Bayesian decision criteria, right? And that is so this will come out to be sigma of a, where sigma is the logistic function, which is 1 over 1 plus e to the power minus a. So this you can easily derive and see that these, if we plug in this particular value of a, what we will get is p of c1. So in particular, what we will get is p of x given c1, p of c1 divided by p of x. And what is p of x? P of x is sum over I. So let's just call it I. So p of x given ci, p of ci. Okay, so here we will have both the terms will be added in the bottom for c is equal to 1 and or I is equal to 1 and I is equal to 2. So these two are equivalent. So this term that you might have seen before, this expression that you might have seen before, is precisely the expression for probabilities of a particular class given the feature, right? If we model A as the log of the ratio of their odds, okay? And it also takes into account their priors. Now here you can notice that this a is still not a linear function of x. So how do we get a linear boundary? It will be a linear function of x if p of x given c1 and p of x given c2 are Gaussian distributions and both have the same sigma. So we can solve for an optimal decision boundary where the two covariance matrices are the same using this logistic expression, and we can interpret this as probability of a particular class given the feature. So to derive the gradient descent for logistic regression, what we need to do is we need to look at p of the t vector. T vector is all the training points that are given to us, and here the training vector is given in form of zeros and ones, not in terms of minus ones and plus ones, because it just, the math works out easier. We will see in a minute. So p of the t vector given the weights, okay, and we want to maximize this particular term for all the components of the vector. So now what is this going to be? This is going to be, we will take the product because of the IID assumption of I going from 1 to n, all right, of the individual probabilities, and those individual probabilities are precisely what we outputted, right? So the sigma that we had computed, the sigma of A, is actually the yi. So we have yi, all right, and why will we have yi? Only when t is equal to 1. So yi to the power ti, and then we will have 1 minus yi to the power 1 minus ti. So what does this mean? that when t is equal to 0, then only this term will matter. When t is equal to 1, then only this term will matter. Only yi will matter. When t is equal to 0, only 1 minus yi will matter. So because we are looking at a binary classification case, what we have is that either we are trying to maximize the probability of the class being 0 or the class being 1, right? And the probability of class being 0 is 1 minus the probability of class being 1. Okay, so what is yi? Yi is the probability that ti is equal to 1 given xi and w. Right? So now if we take a log transformation of this particular expression, we'll get summation for all training points. Now why do we take log transformation? You can see that the log transformation is a monotonic transformation, because of which the convexity property will not change, but we will get an easier looking term that we can work with, which is a summation term as opposed to a product term. Okay, so because we want to maximize that, because we want to convert this into a minimization, so basically what we will get is that we want to minimize over w. Okay, sum over I is equal to 1 to n negative, right? Because we wanted to maximize this, and now we have converted into a minimization problem. Okay, and here what we will have is the power will come down, ti log of yi, okay, plus 1 minus ti log of 1 minus yi. Now what is yi? So yi takes the form of w transpose x plus b if we assume that the underlying distribution are Gaussian for both classes and both have the same sigma. But in logistic regression, that assumption need not be true. We just assume that yi is some w transpose x plus b. So we'll plug that in and we will minimize that expression with respect to w. Right? So you can see that we just need some sort of an exponential distribution, exponential family distribution, with certain parameters to be the same for both classes, and we will get a linear boundary for several of those, and that linear boundary we can solve by using gradient descent on this particular loss, which is this is called the cross entropy loss. Between ti and yi. So think of it this way, that ti is a distribution. It's a very peaky distribution. So if you have ti, it's either 0, completely 0, and there is nothing at 1, or it is completely at 1 and nothing at 0. Whereas yi, it's a Bernoulli distribution, and yi can be an estimate which can have slightly different probabilities at 0 and 1. And these probabilities need not be exactly 0 and exactly 1. So for example, this could be 0.8 and this could be 0.2, right? So this is yi, probability of yi, or yi distribution, and then this is ti, right? So now what we can think of it at this way, that we are trying to bring the other distribution closer to the t distribution, the y distribution closer to the t distribution, and for that we are looking at the cross entropy between the two, and we are trying to minimize that cross entropy. That means there should be no surprises in y given t. Okay, so what is the cross entropy between two distributions p and q? If we have two distributions p and q, basically we are taking the integral of log of q with respect to p and then dx. So these are both distributions of x. Okay. So that's a general cross entropy, the negative of this. So that is a general expression, and that basically is what this particular summation is giving us. And once we take its derivative, and so we will get a very simple expression. Okay. So the derivative that we will get is this derivative of log of w. The derivative of loss of w is going to be something as simple as sum over I yi minus ti, okay, times xi. Right. So and once we plug this into the logistic regression formula, we will be able to do gradient descent and get the solution. Now this particular logistic regression problem is actually a convex problem, and because it is a convex problem, we can, so what is your yi? Yi is this sigma of w transpose xi plus b, right? So because it's a convex problem, what we can also do is we can add terms such as lambda of w squared or lambda of w1, right? So we can add these terms, and these terms will regularize the solution in the sense that they will either keep w small, or they will keep w small and drive some of the w's to 0 to give you a sparse solution. So whatever we had for linear regression, the same kind of regularization can now be applied to logistic regression. And because of this, what we call this sigmoid that we have, it is a linker function that it links a nonlinear problem, which is the classification problem, to a linear regression problem. So it becomes a generalized linear model. So this is a class of problems called generalized linear models.